Hello there, everyone. My name is Anthony Remijan, and I am a scientist at the headquarters of the National Radio Astronomy Observatory, NRAO, located on the campus of the University of Virginia in the city of Charlottesville, Virginia, USA. I'm an observational astrochemist, and I've been working in astrochemistry for nearly 20 years. My research is focused on investigating the physical and chemical environments in the most extreme regions of space. The NRAO is a facility of National Science Foundation operated under cooperative agreement by Associated Universities Incorporated. NRAO provides state-of-the-art radio telescope facilities for use by the international scientific community. Our telescopes are open to all astronomers, regardless of institutional or national affiliation. We also provide both formal and informal programs in education and public outreach for teachers, students, the general public, and the media. It is our mission to provide world-leading telescopes, instrumentation, data, and expertise, train the next generation of scientists and engineers, advance broader, equitable, inclusive participation in science and engineering, and promote astronomy to foster a more scientifically literate society. Astrochemistry. It's this wild cross-disciplinary field that brings together chemistry, astronomy, and physics. And what is our mission? Well, we're trying to explain how all those chemicals out there in space form, where they end up, and just how complex they can get. All right, but what does that really mean? Well, here on Earth, we do most of our chemistry at what is called standard temperature and pressure. You probably heard about this when you were in high school. But imagine this. What happens to chemistry when you are near absolute zero? Or you got just one atom of hydrogen for every cubic centimeter? This sounds impossible, right? Well, you'd think so, but the universe is a bizarre place. Out there we find molecules under the most extreme conditions, and molecules that wouldn't even survive here on Earth. We're talking about these exotic molecules. These molecules sit alongside everyday stuff we find in our homes like ammonia and vinegar. So you could then ask, how do they even form in such harsh environments? Is there a limit to how big these molecules can get? Well, these are the type of questions we are trying to answer. And back in 1969, the detection of formaldehyde was a game changer. It proved that molecules with more than one heavy atom, that is heavier than hydrogen, could actually indeed form in space. So the universe really is a giant chemistry lab, and we're just beginning to understand its potential. You know, the detection of formaldehyde was a game changer. It basically launched what we now call modern astrochemistry. Now, back in the 1800s, astronomers started to use spectrometers to look at space. They found atoms by their absorption and emission lines in the optical region of the spectrum. When electrons jump energy levels, they absorb or emit specific frequency of light, but more about that later. So they knew atoms were out there, and early spectrometers were also able to pick up molecules like CH or OH, one heavy atom and one hydrogen atom. But the big names in the field, even Nobel Prize winners, believe that heavier or larger molecules couldn't form in space's extreme conditions. It took some gutsy young scientists and engineers to challenge that idea. They wondered if molecular rotational spectroscopy, looking at the rotation of molecules at lower frequencies, could reveal more complex molecules in space. But it wasn't easy to get the support they needed. It was a struggle. But they finally convinced the director of the National Radio Astronomy Observatory to give them telescope time. And in 1969, they hit the jackpot. Using the NRAO 140-foot telescope, they detected formaldehyde, the first true polyatomic molecule in space. And that was just the beginning. This discovery started modern astrochemistry, and since then, we've been finding new molecules in space at about 4 per year, mostly through rotational spectroscopy. But since 2020, discoveries have skyrocketed, and we've added nearly 100 new molecules to that list in just 4 years. Their boldness set the stage for a whole new understanding of chemistry in space, and who knows what we'll discover next. This is a very active area of research. There's a big question we're trying to answer. Are molecules we find in the interstellar medium, that's the gas and dust that eventually form stars and planets, inherited directly into the disks that form planets, comets, and asteroids? Or are these molecules continuously recycled, forming and reforming in those planetary disks? And when we look at formaldehyde in comets, it tells us something very interesting is going on. It appears to be a molecular byproduct because formaldehyde doesn't seem to be a major ice component in the comet nucleus. Instead, it's found far from the nucleus, in the comet coma, the part that you see in those stunning optical images. It's possibly formed by the photodissociation of a larger molecule, like methanol. If you expose methanol to solar radiation in space, the radiation can actually strip away 2 hydrogen atoms, turning it into formaldehyde. Methanol just has 2 more hydrogen atoms than formaldehyde, and when sunlight hits it, those hydrogen atoms can be separated, creating formaldehyde. So even the simplest molecules have such complex formation processes in these extreme interstellar conditions. That's what makes this research so fascinating. We're still piecing together the puzzle, molecule by molecule. So in a previous question, I referenced a technique called rotational molecular spectroscopy. That is the way astrochemists uniquely identify molecules in space. To explain the technique, we'll start with the concept of an atom. An atom contains protons and neutrons in the nucleus and a cloud of electrons swarming around the nucleus. So what was found by quantum mechanics is that the electrons occupy very distinct energy states as they swarm around the nucleus. That is, they can have distinct values of energy in those energy states. If an electron wants to move between energy states, they have to absorb or emit the exact amount of energy needed to go from one state to another. Too much or too little, the electrons don't move between states. Because the energy of light is directly related to the frequency or wavelength of light, if an electron absorbs energy, it will take away energy at very specific frequency. If it emits energy, again, it will only emit at a very specific energy. The frequency from electrons is typically in the optical part of the spectrum. Molecules, similarly, have to obey the rules of quantum mechanics, just like energies of electron in an atom. However, with molecules, we're looking at the energy of the rotation of the molecule. And according to quantum mechanics, a molecule can only rotate at very distinct energies. So if a molecule changes energy states by emitting energy, that is emitting light, it will be at a very distinct frequency. Every molecule then has a unique fingerprint of light that it emits. The energy of light being emitted from rotation of molecules is much lower than the energy of light emitted from electrons and atoms. The frequency of the rotation of molecules is at radio or microwaves. Since we first detected formaldehyde in space, we found it in countless other astronomical sources. It's becoming a key tool for diagnosing the physical and chemical conditions of these environments. What's really fascinating is that formaldehyde shows up in both the coldest, most diffuse regions of space and the warmest, densest regions. Trying to unravel the chemical reactions that form formaldehyde in such drastically different environments is a huge challenge, and that's what's going to keep astrochemists busy for years to come. Every new discovery pushes us to understand these chemical processes even better. Well, as we previously discussed, we are still trying to understand if the chemistry we see happening in space can find its way to early planetary systems. However, the discovery of formaldehyde and other molecules in space allow us to start asking deeper and more fundamental questions, such as where did our molecular origins get their start? We still do not have a fundamental understanding as to how the simplest molecules we find in space, like formaldehyde, can grow into self-replicating molecules such as ribonucleic acid, and then how this organization of really complex molecules can evolve into ever more complex systems to eventually become self-aware. Astrochemistry is how we start to answer some of these questions on how chemistry and biology evolve on these early planetary systems. NRAO instrumentation continues to be used to observe formaldehyde for all the reasons previously stated. It's used as a physical and chemical diagnostic to better understand these extreme regions in space. What is most encouraging over the course of the last several years is that we appear to be in a new golden age of astrochemistry. As I previously stated, nearly 100 new molecules have been discovered in space since 2020, and discoveries do not appear to be slowing down. With new telescopes and instrumentation, we continue to push the limits of how large a molecule we can detect in space. What we still need to address is how these molecules got there in the first place. Currently, astrochemical models are largely reactive and can address how molecules are formed only after the molecule has been detected in space. We would like to do better than that. We would like to formulate a chemical model that is predictive. That is, if we know the chemical and physical conditions of a region, what molecules I could expect to find. This is where a molecule like formaldehyde can be very beneficial. We could use formaldehyde to test some of this fundamental chemical theory, and determine theoretically, if I know this region in space very well, is formaldehyde predicted to be there and in what abundance? And if we can achieve this, we would be one step closer in determining our molecular origins in the universe.